Hello, everyone. Thank you for joining us for another live webinar hosted by eTech and All About Circuits. My name is Jeff Child. I'm the editor-in-chief for All About Circuits, and I'll be your moderator today. Today's session is Depth Sensing for Robotics and Logistics, iToF System Design Essentials, and it's brought to you by onsemi. Our presenter today is Aidan Brown. Aidan works within the ICSD division, which is part of the Intelligent Sensing Group at onsemi. He's the product marketing lead for SIPM and iToF products and their global use in the medical and industrial markets. Over the last 15 years, Aidan has worked in various roles, applications, product engineering, test, and marketing across several companies, including Analog Devices, Borns, and onsemi. He has experience working with photonic, inertial, and magnetic sensors. Following the presentation, we'll have a live Q&A with Aidan. You can submit your questions at any time during the webinar using the Q&A section that you can see on the right-hand side of your screen. You'll also find multiple resources from onsemi in the Handouts tab, and you'll be able to access a downloadable copy of today's presentation near the end of the session. I'd also like to remind you that we're going to have several poll questions during the presentation, so keep your eye out for those. I'll be back for our Q&A session, but now I'd like to hand it over to Aidan to begin his presentation.
Hi everyone, my name is Aidan Brown, our product marketing manager for the depth sensing products within the ICSD division of the ISG group at onsemi. I'm here today to talk to you about depth sensing for robotics and logistics and iToF system design essentials. So our agenda for today's webinar, we're going to cover a little bit of an overview of the ICSD group so you can see what our division handles in terms of sensor content. We're going to look at why depth sensing matters for robotics and industrial applications. We're going to see where iToF fits into this. We're going to look at the system level design trade-offs. We're going to look at some real world lessons. We're going to talk about some of the evaluation tools and ecosystem available. We're going to then have a summary and there'll be time at the end for some questions.
So I'm part of the Industrial and Commercial Sensing Division, part of the Intelligent Sensing Group, which focuses on image sensors at onsemi. And we are the market leader in performance imaging. We're the industry's growth leader for robotics, scanning, defense, automotive. We're number 2 for security for non-China markets, and number 2 in machine vision. Some recent highlights, we've sampled our Hyperlux HD product. We've acquired shortwave infrared or SWIR, and we have won several awards for our technology. We have focused on high growth and high performance applications. And in terms of new product introduction, we've introduced 5 new families in 2024 and 3 in 2025. We have a fairly resilient supply chain offering long product longevity, and we're a US-based company. Recently, we've expanded our portfolio to include iToF, our indirect time of flight, ultra high resolution sensors, and shortwave infrared or SWIR technology. And we're continuing to invest in leading edge technologies and manufacturing. That gives us the competitive edge when it comes to application specific designs, expanding ecosystems, world-class development tools, including our industry leading DevWare software for image visualization and tuning, and best in class imaging. And what we're seeing with our portfolio of sensors is that we have expansive growth in industrial and commercial applications. So some of these applications are for smart building and cities, such as security, smart home, future retail, access control and scanning engines, and also for industrial automation for machine vision, factory inspection, factory robots, AGVs, AMRs, logistics robots, and inventory management.
So why does depth sensing matter? If we look at this graphic on the right-hand side of a typical factory automation workflow, we see inspection lines, robotic arms, vehicle loading, AGVs and AMRs. All of these systems need depth. For a robotic arm and pick and place machines, depth is used to find and grab objects. For inspection lines, depth is needed to find defects. In these cases, just using image sensors to look at the visible may not be sufficient. AGVs and AMRs need depth to map the floor of the factory and to navigate. And for vehicle loading, they need depth to measure dimensions and to optimize the loading of the vehicles. So there are many different techniques that can be used for depth sensing, including stereoscopic vision using image sensors, indirect time-of-flight LiDAR, direct time-of-flight LiDAR, and FMCW LiDAR, ultrasonic sensors, and radar. And we can see here that onsemi has a really strong portfolio covering many of these sensors. But for the rest of this discussion today, we're going to focus on indirect time-of-flight. So how does indirect time-of-flight work? So the basic thing of indirect time-of-flight is that we're looking at the phase difference between the illuminated light and reflected light to compute the depth. So we take our modulation signal connected to our laser illuminator, and we output a modulated laser signal that hits our target and gets reflected back to our sensor, where we produce the depth calculation. As I mentioned, we're trying to compute the phase shift between the outgoing laser signal and the received reflected signal. And each point or channel that we're measuring gives us a depth point. So as we can see here in these point clouds, the more channels or pixels that we have on our sensor gives us more points in our point cloud. So having a high resolution sensor gives us a more dense point cloud, which gives us better fidelity of the objects that we're detecting. So to get that phase shift, we need to do 4 different phase measurements. And that is best illustrated on the next slide. So as we mentioned, we're trying to compute the delta or the phase difference between the outgoing and received illumination at the sensor. And to do this, we need to do 4 different phase measurements. Essentially, this is 4 different frames with different delay between the pixel and the illuminator modulation. So we do these 4 separate frames where the light is at different points in the scene, and from this we can compute the phase shift. That gives us the depth at all points in the sensor to all of the objects in our target range, and the maximum range is set by the modulation frequency. So the wavelength choice for time of flight or LiDAR applications is really important. So that wavelength range ranges from the visible 600 nanometers up to the shortwave infrared or 1550 nanometer. And for these, the beam can be visible in the 600 nanometer range, and that may be picked especially for single point applications where they want to see the laser point. But typically for higher channel counts or denser point clouds, you want to use an invisible laser beam. And all of the wavelengths can be used and be made eye safe by design. But in terms of the emitter and detector components, the visible and near infrared have the lowest cost silicon detectors and cost optimized laser diodes. Shortwave infrared does have a large ecosystem of emitters and detector components, but they require higher cost exotic materials, smaller wafers, which again impacts the cost. And if we look at the interference to sunlight, we can see that the shortwave infrared has lower interference than, say, the near infrared or the visible. And the reason for that is plain to see if we look at the solar irradiance model on the right. So what we can see here is the attenuation of the different wavelengths due to the atmosphere of our planet. And we can see that at 1550, a lot of the those photons, or the ambient light photons, are absorbed by the atmosphere. So there's very low amount of noise photons at 1550. It is higher for 940, but as you can see here, there's a little dip in the solar radiance spectrum at 940. So that means that even at high ambient, while we still need to design the system carefully, there are a lot less ambient light photons at that 940. Again, still not as still more than there would be at 1550, but that dip allows us to operate up to quite long range at 940 nanometer. And that, coupled with the large ecosystem of detectors and laser diodes, makes 940 or 905 nanometer very attractive for time of flight applications. So when designing an iToF module, we need to consider the full system. We need to include the TX and RX lenses, the bandpass filter on the receiver, the iToF sensor, and the VCSEL or illumination source. So for the lenses, we need to optimize the lens field of view in combination with any beam steering versus the ambient light, so we enable sufficient power per pixel within eye safety limits to reach our desired range, depending on our modulation frequency as well. We need to increase the VCSEL or the laser source within eye safety limits. On the RX lens, we need good optical path design to minimize any reflections, and optimize AR coatings to reduce glare and other blooming effects that may impact the depth measurement. You also need a bandpass filter. So the bandpass filter will be matched to the VCSEL or laser wavelength, and it also needs to take into account the variation of the VCSEL or laser source over temperature. And on the sensor, then you can optimize the integration time depending on the ambient light level or the environmental light level. In terms of scene illumination methodologies, typically used in DTOF is mechanical scanning or galvo scanners or raster scan. System alignment is a challenge, so are the moving parts, but it is popular for direct time of flight applications, especially if you have a single detector or a small number of detector channels. Beam steering can be very efficient for long range. It offers the best operation in high ambient light, but does require additional calibration. And this is using things like MEMS, liquid crystal waveguides, or optical phased arrays. You can scan on the transmit and receive, or scan on the transmit only. And in this configuration, you'll be operating your iToF sensor more like a rolling shutter style. But again, very efficient for long range, optimizes the power per pixel that you're reading out. And then flash, it's true solid state, primarily for shorter ranges, depending on the laser power, because you're flash illuminating the whole scene. So it can be non-optimal to get the best power per pixel. But it is, again, as I said, true solid state, and you're staring on both the transmit and receive. So depending on your use case, if you're doing short range, flash could be good enough. But if you want to get into a very, very long range or operate in high ambient light, some beam steering may be required. Introducing Hyperlux ID. Hyperlux ID is onsemi's first iToF sensor, leveraging our heritage of image sensors and pixel design, and offers the densest point cloud and highest resolution on the market today for a single sensor. Hyperlux ID is a 1.2 megapixel iToF sensor and it's got built-in depth processing. In terms of features, it's a 1/3 of an inch optical format, It's got 3.5 micron backside illuminated pixels and a high efficient global shutter. And it's got a quantum efficiency at 940 of about 43% and a max modulation frequency of about 200 megahertz. And with the on-chip depth processing, the frames per second are up to 60 frames per second at full resolution and 100 frames per second at VGA. And it's targeted towards different industrial and commercial and consumer applications like machine vision, logistics, robotics, drones, gaming, and AR, VR, to name just a few. And we have designed this sensor to solve several real-world challenges when it comes to depth sensing. One is low motion artifacts, and this is enabled by our unique integration and readout structure, along with the global shutter and on-chip storage. Second is the high depth resolution and accuracy. Again, this is enabled by the high performance 1.2 megapixel global shutter design. Three is the low system cost and small size. This is enabled by the built-in depth processing, so we don't have any frame memory or FPGA or external compute power that's required. Number four is the long depth distance high ambient light rejection. So this is enabled by the iToF implementation, which allows us to range up to 20 meters or 30 meters further than standard iToF and operate outdoors. And number five is coexistence for scalability. So we have on-chip options for interference mitigation. Now I'd like to explore all of these different design challenges in a little bit more detail. So now I'd like to take a look at each of these different design challenges for depth sensing and talk about them in a little bit more detail. So first up is low motion artifacts. So what we're looking on the left-hand side here is when we throw a ball in the air, we can see some distortion of that ball on the top left image using a standard iToF solution. And for bin picking and AGVs, AMRs, anything that moves really fast, we want to maintain the fidelity or the edges of that object as best we can and have very little motion blur. So if we look at a standard iToF sensor, the depth frame, it's doing an exposure followed by a readout sequentially across the entire frame. But if you look at our onsemi sensor, we do all of our exposures up front, and then we do the readout sequentially afterwards. That optimizes the architecture so we get much less motion blur. And this means that we enable fast-moving object detection on belts, conveyors, robotic arms. We get precise 3D recognition, collision avoidance. It can do some gesture recognition, and it can be some wearable products as well. So here we have a short video that I will show that shows the low motion artifacts that can be observed with the onsemi iToF sensor. So in this case, we have a rotating disc with three different objects of various heights. And when compared to the competitor sensor, we show much less motion blur. So I'll just start the video here so you can see for yourselves. And here we see the disc start spinning. And in the onsemi case, the height and shape of those different objects is preserved. But for the competitor sensor, we see a lot of motion blur, a lot of motion artifacts. So high depth resolution and accuracy is really important for many different applications, particularly in bin picking or pick and place machines. So our sensor provides up to 1.2 megapixel resolution and provides both the mono image, the depth map, and a 3D point cloud. And what's really important here is that we can see in the target image that the fidelity or the shape and outline of the boxes, the balls, the hand, and the face are all preserved in the depth, the mono, and the point cloud. And that means that if we're thinking about a pick and place type operation, we can accurately detect the object. We can see some of the fine features, allowing it to be picked up and placed. And this is enabled thanks to the very high efficiency global shutter and backside illuminated pixel technology that drives the performance of the HyperLux ID chip. And it's got again 1.2 megapixel resolution in single frequency mode. It's got that very high quantum efficiency at 940 of 43%, and that enables this really low depth jitter of less than 0.5% up to 5 meters range. And that means that this type of sensor is perfect for inspection and quality control, bin picking, pick and place machines, AR, VR, and some gesture recognition applications as well. HyperLux ID also enables low system cost and small size. If we look at a standard iToF solution, the iToF sensor requires additional resources for depth calculation. That could be using an FPGA or MCU, additional frame memory, and requires a high-speed interface. Compared to the onsemi solution, where we have the depth processing and the frame memory on chip, that means we can output the depth map directly from the sensor. It means less external devices, lower computational power, and more relaxed interface speed. This can help to simplify the system cost, the integration, and maintain small size modules, which are really important for many different applications. The other thing to consider here is the latency. Because the sensor provides the depth output directly, that gives more time on the system end to do something with that data. So if you imagine a pick and place type application where the depth must be measured to an object, the system must then decide, should the arm move and pick up the object? And that must be done maybe if the object is in a box that's also moving on a conveyor. So there are many different timings to consider here, and being able to give that depth data directly to the system minimizes some of the latencies, and it makes sure that when the system makes a decision, it won't miss the object. One main limitation of iToF sensors in the past has been their limitation to short-range only applications. This sensor has been developed to enable long-range detection, and it does this thanks to the dual frequency mode of operation. So here we can have two different frequencies that we measure, and the maximum range is set by the greatest common divisor, or GCD, between those two frequencies. So we can do those two different frequencies, so 8 exposures, all done within one depth frame. So we're not minimizing, or we're not dropping the frame rate. But one thing that happens is that in dual frequency mode, we do operate in VGA mode. Now, you can do some recombination off chip if you can live with lower frame rates, where you can still keep the 1.2 megapixel resolution. So these images here show a nice illustration of that dual frequency mode. It works up to about 30 meters, and here we're seeing operation in high ambient light, up to about 70 klux at the time of the measurement. And here we can see that we're measuring some different white and brown boxes, up to 20 meters in range, and getting, again, good fidelity of the edges of those objects, even in high ambient light conditions. So another really important consideration for mobile robotics and depth sensing is coexistence. So if you have multiple robots, AMRs, AGVs, or depth cameras, they can interfere with each other if they are using the same modulation frequencies. So how can we prevent this? So, if you can utilize different modulation frequencies from each camera, that would prevent this occurring. But that can be difficult to do when you have, if you're outputting a large number of robots or cameras for different applications. So HyperLux ID by default, it enables this spread spectrum approach. And this works by varying the modulation frequency by 1 or 2%. So it kind of varies it over time. And that can minimize the occurrence of interference due to, other cameras or modules with using the same modulation frequency. So there'll always be some percentage difference in the modulation frequency. In terms of evaluation, we offer a 3-board solution: the baseboard, HyperLux ID headboard, and laser board. The baseboard is a Demo 3 evaluation platform, which is the main evaluation platform for all of our image sensors. And the laser board offers up to 4 VCSELs, so we can do from short to long range. And the DevWare software allows you to look at both the 2D image and the 2D and 3D depth map and point cloud. And if you zoom in on the depth, you can see the depth, intensity, and confidence per pixel. And we've developed this eval kit, for many different applications from short to long range. And within the DevWare software, we have defaults that you can quickly select the best fit settings for short, medium, and long range applications. So from short range, half a meter up to 30 meters range. In order to simplify design cycles for our customers, we have also taken steps to develop base drivers, both internally at onsemi and with our partners for different SoC platforms. These include Qualcomm, NVIDIA Jetson, NXP, Ambarella, and Novatech. Please note that these are the currently available released drivers. Customers can request drivers to be added to our system, and we are constantly developing new drivers for HyperLux ID support as well. We also work with many different module manufacturers, and we have several module solutions available for different applications already. So please reach out to us if you want to learn more about our drivers or our module ecosystem. So now we come to the end of today's webinar. I hope you've enjoyed it so far. In summary, we've covered an overview of the ICSD group, why depth sensing matters. We've talked a bit about iToF and how it works and what the principle of operation is. We've talked about some of the system level design trade-offs and some of the real world challenges that can be solved using the HyperLux ID product. We've also talked about the evaluation tools and ecosystem available. And now we'll have time for some questions.
Okay, well, thank you, Aidan, for that fascinating presentation. I know I learned a lot about the role of indirect time-of-flight sensors and depth sensing and the key design issues and the solutions in this area. I see that we already have several interesting questions in the queue. I'll remind everyone that there's still time to submit questions, so just type them in the Q&A section that you can see on your screen. Okay, Aidan, if you're ready, I'll jump into our first question.
Sure, Jeff.
What is the maximum range that can be measured with indirect time-of-flight?
So that's a great question. So there's a couple of different caveats that you need to be aware of, but the main one is the modulation frequency. So with the AF0130 chip, the max range is set by the lowest modulation frequency setting. For our sensor, that gives a range of about 30 to 50 meters.
Got it. How do I mitigate the effects of ambient light?
That's another really important question. So there are a couple of different ways you can do this. So if you're operating in high ambient, you need to have sufficient laser power to reach the targets that you're trying to measure. And LiDAR or iToF is a photon-starved environment where we're trying to get as much signal back from a target to our sensor as possible. So the other way to optimize the laser power is, one, to increase the laser power, but you're going to be caught with eye safety limits. You can reduce the field of view. That maximizes the output laser power per received pixel. Or you could scan. So scanning is probably the most efficient way. Typical iToF sensors are set up for flash operation, where we try to fill the entire field of view with our illumination source. Scanning allows us to be a little bit more targeted with our illumination power. So you can see scanning is typically used in DToF. The trade-off with scanning is that you could potentially lose frame rate, depending on how your scan system is operating. There could be, again, some additional calibration or alignment issues with using scanning. The other thing to consider is the bandpass filter on the receive lens. So that needs to be tight enough that it restricts the majority of the ambient light and is really focused on the wavelength of interest of your illumination source, but needs to be wide enough to compensate for any temperature effects that could change the wavelength of those lasers or pixels. And the other main important one is good optical path design to minimize blooming and other unwanted effects.
Got it. This is an interesting question. Can I use my own depth processing algorithms?
Yeah, so the AF0130 or Hyperlux ID product, it comes in two flavors, AF0130 with the on-chip depth processing, and an AF0131, which doesn't have that on-chip depth processing. And the reason why we have the two is that when we talk to customers, we see a certain amount of customers like to have the on-chip depth processing, but some have expertise and a lot of history and design their own depth processing algorithms. So for those, they can use the AF0131 and just process all the data directly from the chip themselves. But for those who want a simpler solution, we offer the AF0130, and that has the depth processing on chip.
Got it. Do you have a recommended SoC that I could use?
Yeah, so as we covered in the presentation, we're working with all of the main vendors like NVIDIA, Ambarella, NXP, and we have developed, and Qualcomm, we have developed, with them and internally, some base drivers to support our customers. Customers can request new drivers to be added to those lists, and we're always, developing new drivers internally as well.
Excellent. Got a little mechanical issue here on my end. How can I access a module?
Yeah, so please reach out to us if you're interested in getting a module. We are developing a module reference design that should be released later this year, and we have ecosystem partners that have developed modules for general purpose applications. So please reach out to me through LinkedIn or to our sales or applications team on the onsemi website for support. Or if you want to get in touch about modules for various applications, we can talk you through what you need to consider for your specific application as well.
Last question. You kind of answered this already, but maybe you can get more detail. But where can I find out more about these products?
Yeah, so go to the onsemi website, look for the AF0131. We have lots of handouts and system solutions guides in the handouts section of today's webinar. Reach out to me directly. So search for Aidan Brown on LinkedIn. You'll find me. Please reach out. I'd be happy to talk to anybody about our products. If you learn more, you can always reach out to the onsemi support team through our website as well.
Excellent. I'm going to give just a couple seconds for someone if they want to ask any questions. But while we wait for that, Aidan, any last thoughts you want people to take away from today?
Yeah, I guess the main takeaway is that if we look at iToF sensors in the past, they're always limited by range, limited by motion artifacts. we now have this new product from onsemi that is proven in the field, in many different modules for different applications today, for AMRs, AGVs, robotics applications. It can work up to long range. And it's got that on-chip depth processing that just minimizes the module size. So really useful product. And again, it has that those spread spectrum settings enabled by default, so it can coexist with other modules operating at the same light wavelength and frequency.
Excellent. Well, Aidan, thank you so much for the presentation and this great discussion during the Q&A. In just a moment, you're going to be redirected to onsemi's website. You'll be able to watch this session on demand anytime by using the same link that you used to join this webinar. So I want to thank you, Aidan, and thank you all for participating. We look forward to seeing you all at another live session hosted by eTech and All About Circuits.
Thanks, Jeff, and thanks everybody for attending.